In the last video, we looked at the full picture, 3 stages, 3 output, 1 pipeline. Now we go deep in pre-training. Before a single weight gets updated, before any training happens at all, someone has to answer one question. What do you actually feed it? The answer is most of the written internet, but not raw, not just dumped in. A good well-processed internet text. If we put garbage in, the model will give garbage out. There's a pipeline that runs before even training starts, and the quality of what goes in determines the quality of what comes out. Let's walk through it. The data starts here. Wikipedia, books, GitHub repositories, Reddit threads, news articles, research paper. This is the whole internet data we scrap. Now let me give you a scale of this. GPT-4 was trained on roughly 15 trillion tokens. A token is roughly 3/4 of a word. So we are talking about approximately 10 to 12 trillion words of text. For context, if you read 8 hours a day, every day, it would take you over 50,000 years to read what GPT was trained on. So basically, GPT-4 was trained on the whole internet. Most of the internet is noise, spam, duplicates, low quality content, garbage, HTML, tags, cookies, etc. You don't want to feed that stuff in your model. So the data has to be cleaned, and that cleaning happens through a pipeline, and this is the pipeline. This is FineWeb pipeline built by Hugging Face and open source. It's one of the best documented data pipelines for LLM trainings, and a lot of modern models use this as a reference. Before downloading anything, non-spam domains, adult content sites, malware sites, low quality aggregators, they are all removed. We remove them at the start. We don't want that content. Then comes text extraction. Web pages are HTML, full of tags, navigation, menu, ads, etc. You don't want any of them. This step strips everything, leaving just the raw readable text. Language filtering detects what language the content is in. Models are trained with intentional language ratios. Then comes gopher filtering. It's basically a set of quality rules developed by DeepMind. Things like, does the document have enough words? Is the ratio of punctuation to text reasonable? Does it look like real prose or just a list of keywords? Removes low quality machine generated or scrap junk. Then comes mini hash deduplication. The same Wikipedia articles get mirrored on thousands of websites. The same news story gets republished everywhere. Mini hash is a fast algorithm that finds near identical documents across billions of pages and removes the duplicates. If the model trains on the same text thousands of times, it memorizes it instead of learning from it. That's somewhat called overfitting. We'll cover that in the next videos. But basically, this removes duplicate content in the dataset. Another set of quality rules originally from Google's C4 dataset removes pages with offensive content, placeholder text, code-heavy pages without explanation, and pages that don't end with the proper punctuation. And there are some custom filters of AI labs which they use on their use case of the model which they are training. For example, an educational model does not need the sports data. So that's somewhat custom filtering. This is very important, the personal information removal. You don't want an LLM to train on someone's personal information and then leak that information. So this is very crucial. What comes out of this entire pipeline is clean, filtered, deduplicated text ready for the next step. But here's the thing, the model doesn't read text. Not a single character of it goes directly into the neural network. It all has to be converted first into something called tokens. Now this brings us to the next question. Why token exist? Why not just feed the raw text to the model? Why not feed individual characters? There are two reasons. Reason one, character level is too slow. If you work at the character level, every word becomes a long sequence. A 500 word paragraph becomes thousands of steps. The model has to work extremely hard to connect meaning across that distance. What this means is hello becomes 5 tokens. The model has to work extremely hard to connect the meaning across the distance. Training becomes painfully slow and inefficient. So that's first reason. Second, word level is too big, and if you work at the word level, your vocabulary explodes. Every language, every technical term, every name, every variation, every misspelling, you don't need millions of entries in your dictionary. So character level is too small and word level is too big. Tokens are middle ground, chunks of text bigger than character, smaller than full words. Sometimes that gives the model manageable peace without an unmanageable vocabulary. So these are the two reasons which led to the generation of tokens. What does token look like? each color coding is a different token here. Let's understand how this dictionary is made. The token dictionary is built using an algorithm called Byte Pair Encoding (BPE), and the way it works is simple and elegant, just 4 steps. Step 1, start with individual characters. Every unique character becomes its own token. At this point, hello is 5 separate tokens, which we already discussed. Vocabulary size is 256 if you start from row bytes. Step 2, count all the pairs, merge the most common one. Look at every pair of adjacent tokens across the entire training dataset and see which sequence of token is repeating multiple times. For example, maybe LL appears millions of times in hello will called all. Merge it. LL is a single token and this shortens the data size. What it means is, for example, let's take WWY. Let's say that this is our entire training data set and we can see that WW is occurring the maximum number of times. So we would replace WW by capital W. The sequence of our training data set becomes capital W, Y, capital W, Y, capital W, Y. Now we can see that WY occurs maximum number of time. In the next iteration, we would replace WY by a single token Z. So our data set becomes Z, Z, Z. So you can see that from this big dictionary, we got to only 3 tokens and the process goes on. So step 3 is keep merging, repeat thousands of times. Each iteration find the most common pair, merge it, add to the vocabulary. He gets merged, the gets merged, ing gets merged. Common words start appearing as single tokens. Stop when you reach your target vocabulary size. GPT-4 uses a vocabulary of 100k tokens. The number isn't random. It's the result of running BPE until the vocabulary hit the balance between size and coverage. Now, byte pair encoding is not the only way to build token dictionary. There's another approach worth knowing called sentence piece used in models like Llama and Gemini. The core idea is similar. You can go to Google and just read. The core idea is same. Let me show you all this live now. This is the Tick Tokenizer, a free tool that shows you exactly how GPT-2 and GPT-4 tokenize any text you give, and it has multiple token dictionaries. You can play with them. Let's start with GPT-2, the older model. I just put a segment of code here. Every single space is its own token. In Python, spacing is everything. 4 space, that's 4 separate tokens. 8 space, 8 tokens. The model is burning through its context window just on white spaces, and the model has to learn that continuous 4 space tokens in a row means this is inside a function. That's an incredibly inefficient way to represent code structure. Now let's see in ChatGPT-4 token dictionary. See the difference? All these spaces got merged. GPT-4 BPE ran on a dataset that included a massive amount of Python code, so the merging algorithm found that those space sequences appear constantly together and merge them into a single token. If I just keep on increasing the spaces, the token count remains still the same. GPT-4 represents the same Python code in significantly fewer tokens, less context used, more efficient, and the model's internal representation of code structure is cleaner. This is practical impact of a better token dictionary. It's not just an implementation detail. It directly affects how well the model handles the certain context. Now let's play with a little bit of English here. Each color is a different token. Common words like the and over are single tokens now. They appeared so often during byte pair encoding that they earned their own entry in the vocabulary. Now let's take a word which is not that common. Unbelievable. 3 tokens. Unbelievable. Now none of them are full words, but they are most efficient subwords chunk that covers this word given the training dataset. And let's play with a little bit of numbers. This is part why LLMs struggle with arithmetic. They are not calculating, they're predicting token sequences, and 2 as a token doesn't carry the mathematical meaning of the number 2. This is what every piece of training data looks like by the time it reaches the neural network. Not text, not characters, but numbers. The neural network sees this sequence, not this. When you enter plain English, that plain English gets converted into tokens, and this is fed to the neural network to process. These tokens are also converted into embeddings, but that's a separate conversation we can have. But for now, understand that every prompt gets converted into tokens, and this is what LLM read. In part 2, we go inside the neural network and see what actually happened to those numbers which I just showed you. How does a model go from a sequence of integers to something that understands language? See you in the next video. Follow for more.